Thibaud, you check if workers,
I mean, I did.
Thibaud, there is a problem with the marker.
I think that's
The black marker.
even that's not I had done it before.
No, that's fine. I guess it's just.
And now it works.
Sorry, I did a lot of this.
I think same strategy. So
E Marco,
new plan. People will talk.
Thanks for the great introduction, Bob. Thanks a lot. I would like to thank a lot the organizer for this amazing meeting for inviting me to attend first and to speak. I will say that this is my first talk at a conference like this, so that's perspective the nerves. Also, this is work in progress, so this doesn't help with the nerves, but I hope you will all have something take something interesting out of this talk. So I will be talking about current ongoing work with my advisor, Daniel Mazacz, and collaborator, Jakub Boschnera, around new boundary state in the Narain CFT. So kind of the big picture program around this, I would say, is comparatively we understand 2D CFTs much better than higher D CFTs, but there are still lots and lots of that we don't know about 2D CFTs. A major problem would be to construct examples of, say, compact irrational. So for today, with C bigger than 1, say, CFTs and interacting with non-free, which is a hard problem, with only Virasoro chiral algebra. It's a problem that's pretty much wide open, from what I understand. I mean, there's obviously some people in the audience are working on these things. That's of course like Antonio and Connor, and Junchen. Thank you. Actually, this week, addressing this. So this is not exactly what we'll be addressing. What we'll be addressing is compact irrational C greater than 1, in some C greater than 1 theory, finding some compact boundary condition which only preserves Virasoro chiral algebra. So C greater than 1 boundary condition only preserving Virasoro. Okay. So that's, I guess, a broader context than just this one theory. So why do we focus on this one theory? Well, pretty much it's the
Compact here means
a discrete spectrum.
Okay.
Yeah, discrete spectrum. Sorry. Thanks for the question. Right. So why this guy? Why C equals to Narain? Well, I will spoil a bit of the punchline of this talk, but what I will present today is a perturbative setup where the conditions for this setup to arise are that we need some marginal deformation in the CFT, so conformal manifold, around a point where a boundary operator, I will review this in this case, but a boundary operator has dimension 1 minus a small correction. And we're going to take this correction to be arbitrarily small. So that's why this assumption is useful. And with, let's call it V, and with boundary 3-point functions positive. So we'll be using some input from conformal partition here. And this is the assumptions we need to make this work. And C equals to Narain is the simplest setup where we can realize this. Central short beacon. All right. So now, there are no questions at this point. I will move on to describe the setup more precisely and tell you kind of how far we got so far and what we're doing currently and hope to do next. But the upshot is that we'll see a new boundary. So something satisfying this starting to appear. Pretty convincing evidence that it's there. So, after this. So I will be quick because I'm sure most of you know all of this already. But C equal to Narain CFT describes three bosons compactified, two free bosons compactified on a lattice. So action looks something like, you know, with some metric of this variable x new. And we'll pick the simplest case where the setup applies. We'll pick a point, well, we'll pick a lattice, which is the triangle lattice, the regular triangle lattice. So that what it does for us is that we have a discrete dihedral symmetry of the spectrum coming from the isometries of this lattice. Right, so the bulk spectrum of this theory is completely well understood. There's a U1 squared winding times U1 squared momentum chiral algebra. So the winding is, yeah, so this describes, if you want a sigma model with target space of torus. And so you can wind along the two cycles of the torus, and there's some certain mass momentum. And yeah, so that's the bulk model, and the spectrum arranges in primaries for this chiral algebra, labeled by a winding and the momentum quantum number. So the winding is an element of this lattice, and the momentum an element of the dual lattice. Okay, so that's the bulk theory.
Are you not writing the B field on purpose because you won't use it, or?
Right, so we'll study at 0 B field. That's a good point. I should mention this. Thank you. So our point is 0 B field and this geometry, and we will vary the volume of the torus as a parameter. So this will determine our y. Any more questions at this point? Good. So the most well-known boundary conditions of this model are combinations of Dirichlet and Neumann boundary conditions for at this level, which I will label by the corresponding dimension of the branes in string theory. So we have a D2, what I'll call D2 boundary condition, where both of these are Neumann. There's a D0 where both of these are Dirichlet, and there's D1 where there's some combination which is Neumann and some combination which is Dirichlet. So there are several of these guys oriented along distinct cycles of the torus, which are well understood. And this comes in families. So for instance, the simplest one is this guy. We can put this D0 anywhere on the target space torus that we want. So we have the two parameter family of boundary conditions here, two parameter family here, two parameter family here. And this position is labeled by an element of part of this chiral algebra, which is broken by this boundary condition. So Marco told us a lot about the C=1 case on Tuesday. So here it's really similar. So this breaks half. Well, all of these break half, but this one's this one breaks momentum, and this one breaks winding completely, and this one has some combination. But these don't break all the way down to just zeros. So this is not what we're looking for. So what we'll do is we'll start from this guy, purely Neumann, and we'll turn on some deformation, some boundary interaction, and study what happens. So the boundary spectrum of this boundary condition is labeled by the dual lattice. So the momenta quantum numbers, and the U1 squared prime, like labeled by some momentum, and this label U1 squared boundary primaries, which are basically the restriction to the boundary of the vertex operators to the IKX for k in this momentum lattice. And we know exactly the dimensions of this guy. These are given explicitly, say in terms of this metric, by up to some, yeah.
The primaries of your continuity.
Right. These are primaries of the remaining U1 squared current algebra. And so, okay, aside from the vacuum, the minimum, there's a gap, and the minimum guy is given by this for the shortest length so far, say 1,0 vectors in these components. And it's something like, I can write explicitly. R here is the radius of one of this cycle on the torus. K1 squared minus K1 K2 to K2 squared. So
Will we change market?
yes, I can change markups. The main point is that there is a magical radius where the minimal such guy has dimension exactly 1. So I'll call it R star. It's this radius where the gap is 1. And so there's 6 such primary operators labeled by the dual lattice, which is also a triangular lattice. And what we do is we include the boundary deformation by an operator V, which is just the Z6 symmetric combination of these guys. So we do this just to preserve this symmetry in the new boundary state. This is not strictly mandatory for the setup to work, but it just simplifies the problem. And it will simplify a lot. So we will still be able to organize the spectrum in terms of D6 representations, and this will help a lot in terms of computing anomalous dimensions and these kind of things. So now the goal is, okay, Marco reminded us what are the observables that we care about in boundary CFT.
So you have 6 of these operators then.
That's right. So I just perturbed by the symmetric combination. But the most general we can do is say a sum over, say I label from 1 to 6 these 6 momenta. So a sum over Z6 of some root of unity to some power times e to the ikx to diagonalize the rotation by 6 of the turn. And okay, then we disarrange it to multiplets for if you also include the reflection. So these are the guys for which we'll compute the deformed spectrum precisely because this is the simplest. And O0 is big.
Yes. I'm more familiar with C plus 1. Here,
Right.
When you have 2 bosons, do you also allow some weighted modes to give dimension 1?
Somewhat.
When you see plus 1, you have weighted modes, right?
Winding modes.
Yeah.
So okay. So this is the boundary spectrum. Marker is also not good.
Bro, the ones thrown back at the electron, so like.
This one seems to want so down. Yeah, perfect. Spectrum on purely Neumann. So in the open channel, it's only momentum. In the closed channel, it will be only winding. Yeah. Yes. That's right. Closed, it's purely winding. Thank you. Right. So what are the? Yeah. And so we'll deform this, and the point is that as we increase the radius of the torus, this dimension, this radius above this R star, the dimension of this unit norm of this primary corresponding to unit norm momentum will go a little bit below 1, and so it will become slightly relevant. And so another point is that if we compute the 3-point function of this guy, you see this still, right? This is positive. This is actually root 2/3, if you want, at this point. And so we have positive 3-point function and a slightly relevant operator at positive y at r bigger than r star. And so this will trigger a short RG flow, and we can study what happens in the IR using conformal perturbation. So that's the strategy. And so what observables do we care about?
So you think your radius is a little bit
bigger.
A little bit big.
Yes.
Sure.
Yeah. So this is 1 minus y. So I increase y, so I reduce r. I increase r. So the observables we care about are
Sorry, stupid question.
Yeah.
So this operator at momentum one,
right.
and it,
Well, it's normal. Yeah. Okay. So what's your question?
I think it's a superior question probably to what you were gonna say. Why the tripling function is non-zero if you are only charged one operator in this linear combination? How do you sum it up to zeros?
So yes. So I'll draw a picture. So this guy is a linear combination of all 6 of these momenta.
Yeah. So
So I will have something trilinear, and so this combination will be non-zero.
yeah.
And then 6 of the 3 of them will be non-zero. So this is how it is. Yeah. So and then basically you cannot kind of intuitively, this is why we need at least C equals 2 to be able to draw this triangle. Yeah. C equals 1. We don't expect that anything like this can happen. Right. So what we care about are the infrared boundary scaling dimensions and the boundary state coefficients that Marco boundary OP, both boundary say OP coefficients that Marco reminded us on Tuesday. We also care about the other data that Marco introduced, but so far we focused on this, on these. Yes, so these will be given by the ones for the D2 plus corrections as a series in Y, and yeah, so it'll go
halfway timeless.
Sure. All right, so I will move to what's predicted using the CPT, and then once still ongoing. So what we have done, what's previous. So the big upshot of the CPT analysis, which I will detail a bit, is that we have 4 dimension 1 operators, primary operators, to the order that we could compute. So far, this is at order y squared in CPT. So why is this important? Yes, you have a question? Okay, why is this important? Well, let's go back to what I said before. So say we have this boundary condition, it's labeled by a position on a torus, and moving it around is a marginal deformation of this boundary condition, which is associated with the broken U1 squared symmetry. And so this corresponds to a dimension 1 boundary operator. And in general, this kind of dimension 1 boundary operators you can think of as Goldstone modes for the for the symmetry that the boundary condition breaks. So here, since we're breaking the full U1 squared times U1 squared down to Virasoro, we expect 4 boundary operators. Geometrically, just as this guy is labeled by position on a torus, you can think as this guy as being labeled by position on the dual torus. And so what I'm saying is that, but this guy is kind of uniform on the dual torus, and this guy is uniform on the primal torus. This guy will be uniform on neither. Basically, it will be not translation invariant, neither on the primal or T-dual torus. So how do we do this? Well, at first order, we have yeah. So we have checked this basically using CPT. So I can tell you the precise operator content. So what could go wrong? Like, which ones? Where are we looking? We're looking among these norm 1 guys plus the 2 currents, the 2 level 1 descendants of the identity, which are the currents dx and dx1 and dx2. And so, first off, there is yeah. So this is a perturbation theory problem. So what you do is there will be a matrix of anomalous dimensions possibly. so in the UV, the dilation operator is diagonal, but it could happen that along this flow, we need to re-diagonalize it. But in this case, it does not happen. There's no mixing. It's also something that checked. Yeah, and so to have dimension 1 operators in the IR, we look for things which are dimension 1 at y equals 0 in the UV, and we compute the anomalous dimensional flow. So I will note all of it if you want. But yeah, the result is basically.
Sorry, the two H equals 1 operators that we interpret as Goldstones at the free fixed point are just dx.
Just dx, yeah. So yeah, so these are, I should write this. These are dx mu, and what they call O plus or minus 1. Here this J is in Z6.
So in the language that Thibaud was using, this would be tilt operators.
These would be tilt operators. Yes, I should also mention this. Thank you. And you can, an easy way to see that these are the correct ones is you can just write the classical equations of motion with this boundary interaction, and pops out that this guy, the constraint is that the derivatives are combinations of these two guys. So it's kind of a hint that these are the same charges as the currents. So let's say we're able to.
Sorry, but is the game now that you want these to be or dimension exactly one
Yes.
orders in perturbation theory?
Yes,
This
yeah.
boundary.
And so far we've been able to check the leading and next to leading order, which works. So this
Because
is
that is the indication that this boundary condition does not preserve
correct.
these those two.
Correct. Yeah,
And then, sorry for hijacking a little.
That's fine.
But then so even if that is true.
Yeah.
Can the boundary condition be secretly rational in the sense that it preserves something crazy, some crazy sub-algebra of the bulk algebra still, or would the all orders, if someone just tells you it's true to all orders, or maybe even non-perturbatively, then is that automatic, then that this boundary condition is one of the type that you searched?
I don't think I have like an easy answer off the top of my head, but
Because it contrasts a bit with the bulk analysis where we search for irrational CFT starting from a rational point, and then you need infinitely many currents to lift. And here you just need you have.
yeah, sure.
It's like you have
Yeah.
infinitely many conditions to check, and here you seem to have.
I guess
two conditions.
the only loophole is that they could be marginal operators that come from something else.
Yeah.
No, from down below in the U1 module. I think that's what Bob is saying.
But new
So higher boundary
Issue
dimension.
that they can't be interpreted as Goldstones.
But-
You'd like to show that they're actually Goldstones.
Oh, there's that.
Yes.
Anyway, we should.
Yeah.
Yes. So, for instance, the point where you started with, there is an extra boundary operator of dimension 1 that has nothing to do with that, with the tilt, right? Which is this operator that is using flow. So if you were to just count operators at dimension 1, you would be fooled. Yeah, right. For instance.
So it's dimension 1 at the undeformed, but
Again, it works. So then you had a comment that addresses that already, which is the charges. But you could also, in cohort perturbation theory, compute about boundary coupling with the bulk currents, and
yes,
then check if the doing condition is disobeyed.
yes, and
Then you-
yeah. So it's not at first order, which is what we have. So this side is also consistent. How much time do we have left?
Give you 10 minutes, but 3 minutes, technically 7. But
Okay.
we go over.
Yeah.
You can still admit from your position.
So yeah. So the way you compute this, at least at first order, it's the story is quite well known, and this correction here. So what we actually do is organize in terms of UV plus corrections. And the first order is given by So you look stare at this interaction, and so you see that the first order it will come from 3-point functions of two of these guys with the diffuse. So the precise thing is that this is here. Theory is free, and the UV boundary condition is this is at y equals 0. Is very simple. So this is easy to compute. And okay, I will the anomalous dimensions are basically I'll list up to order y here. So this order is no, so I think here.
Well, sorry, isn't it clear what the marginal operator is? It's changing the phase. Right? You're explicitly breaking translation symmetry.
Yes.
That's the thing.
Yes. Yeah.
And so the Goldstone mode is just the phonon. I just multiply that.
Sure.
I think there should be a way to prove to all orders that it has to be marginal.
If you are breaking those symmetries.
But
Yeah.
explicitly breaking or adding to the actions, but IKX.
I mean, that's what Seals do. Yeah.
Mhm. Yeah. Yeah. So I guess what do we have in mind next? So the dream is to isolate this guy completely, say using annual processing, using points and line bootstrap, these kind of things. But obviously, if you only input the bulk theory, there's kind of no hope that you find this guy precisely, because one other natural observable is this guy when both of these are the identity, and this is the G function that Marco talks about. And the G function is kind of DUV minus some universal, some correction, which we know explicitly times higher order. The point is that it's going to be below the Neumann G function. And so if you do just annual bootstrap with only bulk information, kind of the upper bound will have a hard time going below this Neumann. It's not okay. But if we also input some information about the boundary state, say that some of these guys are exactly at dimension 1, or as much information as we can, the hope is that then this will let us isolate this guy much more precise. So that's kind of the upcoming thing that we would like to do is to bootstrap this guy as best as we can, using as input this kind of computation. We also have a next to leading order prediction in CPT, which I'm sure some of you know is much trickier, based on some ongoing work from Jakub with Tien with straight field theory data. So as Marco also mentioned that there's this interaction between the search for boundary conditions in 2D CFTs and this community in open string field theory. And in fact, parallel to this story there, and actually inspiring our work, there's this work by Jakub Boschmera, it's the name so long, Martin Schnabel and Matej Kurlena, who are kind of studying the same system in OSFT and finding flow certifications for this guy here. Yeah, and so far, I guess I should wrap up soon.
For 5 minutes.
Yeah. Okay. So we also have, say, CPT predictions for these guys at leading order and working on the next leading order. And the point is, we can input this into the annuals bootstrap and then into the 2-point false boundary bootstrap to hope to nail this theory. So let me stay next. Sorry about rhythm. Right, so maybe I can also say that the current state of the annuals bootstrap numerics kind of thankfully does not rule out this guy, but it's was expected. Yeah. So let me give you one, like the most recent plot. So this is, so what you're looking at is a partition function with this boundary condition, they call it beta on both sides, on an annulus of length t. On one side, the closed channel, you will see propagation of the boundary state corresponding to this thing. And on the open channel, you will have trace over the open spectrum space. And as Marco reminded us, this is an expansion with positive coefficients on both sides. It's a good bootstrap problem. And the state of the art numerics right now is this plot. So I'm plotting, so I have R slightly bigger than R star. And I'm plotting the G function as a function of the H gap, which is the dimension of the first boundary frame.
But we put in R. What, how do you input R?
The bulk theory knows what R is. Yeah. So story, our perturbative parameter is kind of a deformation of the bulk theory, but it's marginal. It's like it's just increasing the radius of the terms. So this knows about R. And so the plot looks like this. We have an exclusion now and some kinks. So it's very similar to the Mark or on Tuesday, obviously, for C equals 1. And we have some known, this is not correct, some known data points. So this is the D2 that we're starting from. Here, there's the D0 that I mentioned before. Here's some D1, and our guy is slightly smaller G function, obviously, and lower gap, because on the D2, the gap would be set by y minus y, and on in this guy you have a more relevant this, so the gap will be smaller, and that might be something below that. But
in this plot, are you only putting C equal to or a bunch of bulk operators?
No, we're putting, so we're using this theory. So we're putting some bulk operators, 18 bulk operators for this particular plot.
That's why the kids, right?
That's right. Yeah. So it knows about the bulk. Yes, it's not a universal plot for this bulk theory, and we expand around the self-dual points to some number of derivatives. So this does not rule out, I think, but based on the shape, it's not that surprising. But some indication that so far it's not wrong.
Do you make an assumption that kills the D2 boundary condition?
Well, that would be the existence of 4 H equals 1 of say accounting of this number of guys would be something that kills it.
But that's hard, right?
when we know which ones are candidates, and we can check that which ones get corrections and which ones don't.
So in the others, we can just put 4.
Sorry?
In the others, we can just put 4
You
to
can do
the down beta, but
yeah.
Well, you have to arrange in terms of Virasoro primaries, so you need to worry about E1 square descendants. But yes, sure, we can input the precise number. But in this case, it's 4 precise, 2 class, and this guys. That's right. So yeah, next step is prove this, include the boundary OBEs, as Marco told us on Tuesday. Is a good thing. Yeah, one thing that I mentioned but did not write yet is that we have predictions for next orders. And I think this will be interesting upcoming work. So like Jakub and collaborators on how we precisely we can have a systematic prediction for next to leading orders in PT. What else do I want to say? I want to say that more generally, there's this setup with a marginal bond deformation. It's kind of nice for exploring properties of these boundary states. So in the spirit of Rajiv's keywords, let me tell you what we are motivated to do and what could be done next. So delta I already kind of covered, which is Bush, these numerics, to kind of try to nail down this guy precisely. In terms of breadth, some interesting observables that we can look at are, for instance, annual partition functions with 2 different boundary conditions to tell us about the spectrum of boundary condition changing operators. This is also something that can be done, and we can get some predictions from this setup and try to input this into to have more observables into this Bootstrap problem. Yeah. So say the alpha and beta for 2 different boundary conditions, and so here you would put ones that you already know. For instance, something else is we have made sure in this particular model to preserve this symmetry to help us, so we can also try to extract symmetry refined information if we want. And I guess for perspective, then it's up to creativity to find instances where the same strategy is applicable to try to look for new boundary states, right? So here we have taken this specific shape, but really close neighbor would just be C equals 1 tensor C equals 1, so the rectangular torus. And this would tell us something about conformal line defects in the C equal 1 theory, which is not from my understanding, not such a well-known story. There's and some other models with this kind of bulk marginal deformation we could also hope to look for non-maximally symmetry preserving boundary conditions using this kind of techniques, which so to me is a interesting outlook for this method. With that, I think I will stop here. If you have more questions, then you're welcome to.
So I vaguely remember the context of studies of open strand tachyon condensation. There's this thing called the rolling tachyon boundary state, which is an exact boundary state in C equals 1 theory, where which describes the deformation on the boundary by Cosh of X. So you want to, but okay, never mind about this. Sure. The point I want to make is that I think there's some exact expression for this boundary state.
So
Deforming C equals 1 way. Let's forget about the cost. Let's think about cosine.
Right. So I forgot to say, but I should have said that there's been some previous related work in a very different, so motivated by quantum Brownian motion by Affleck, Masaki Yoshikawa, and Robert Saller at a different radius, so at radius square root of 2. In this case, the same deformation is integrable. Yeah, and you can, so then they have some exact solution. So we're studying it at a different point in the bulk moduli space. But at some point it should connect to this solution. So obviously from the perturbation theory, it's kind of not obvious how I will connect, but
And people make it sound scary. I think
Don't solve all.
using the fact that you're starting from a free theory.
yeah,
Yeah, so I think
yes, it's.
I think we should, time is almost up, so we should give people. So
Yeah.
if there's another last question. All right. Thank you again. So do you want to go downstairs? We have 3 minutes in. Just whatever it was. Sorry, I don't.
I guess my question was interesting. It's okay.
Not there.
Yeah, it's good. Yeah, I don't see the point.
But because there is this thing on.
I shot just remove it.
I mean, just turn it off.
Yeah, that's the-
I think one.
Yeah.
But I mean, we're
just-
just done.
That's fine.
But
that's fine.
Yeah, finish this.
Yeah, we have it. No, but
That you can take really well. From now on, you're going to be.
I know we're not.
On an arbitrary manifold has put very non-trivial constraints on the CFT data. And the most prominent example is probably model invariance, the torus partition function in 2D, which gave rise to the Cardi formula. And also, similarly, in a study of 2D CFTs, the modular invariance of genus 2 partition function has led to a universal equation OP coefficients between heavy operators. It is then a natural question to ask, what about higher dimensional CFTs? What can we learn about the CFT data by trying to define such CFTs on a higher dimensional analog of a genus 2 manifold? So maybe I should start by defining what is a genus 2 manifold. Well, it's simple. It's simply the connected sum of S1 times ST minus 1 with a sub. Sharp here basically is taken from that sum. So the study of genus 2 partition functions in higher dimension is actually initiated in this paper. What I'm going to present today can be sort of as an extension of the discussion in this work. And this is still work in progress with my supervisor, David's study. Yeah.
Should we think about it? But is there a constant negative curvature metric on it, like there is in 2 dimensions? In 2 dimensions, there's a canonical metric on the.
Yeah. In 2 dimension, there is a canonical metric on the moduli space of such.
No,
such manifold.
itself.
Oh, yeah, also on this manifold itself. In high dimension, well, actually, what we care about are the flat conformal structures, which is an equivalence class of conformally flat metric on such a manifold.
There's a conformal flat metric.
Yeah, yeah, so I will ask the question, since you asked the question, I guess, I will start my talk by explaining how to parameterize the conformal flat structures on such a
I'm
Um,
familiar with this notation.
explain about this notation.
Yeah.
So this notation means you have two pieces S1 times SD minus 1, and you're taking their connected sums.
That picture.
Sorry, this.
Yeah.
Yeah, it's basically, the connected sum is basically referring to this picture. So what I will do is I will construct the genus 2 manifold in two different ways, in two different cutting and gluing readings, schemes. The first one is by, well, the connected sum.
Yeah, but what's the connected sum?
Oh, what's a connected sum? Okay, so if you to build a connected sum, you remove a d-dimensional ball from one copy, remove another d-dimensional ball from the other copy, and then you connect the boundary of the two d-dimensional balls by a cylinder.
Okay.
By cylinder, I mean as r times distance. That's the definition of things.
Thanks.
Okay. So, oh, but since this is a short talk, I will do this following trick of spelling out the most important equation at the beginning of the talk. So
That's also a good idea for a long talk.
I guess almost said. But what is this good for? Well, as an immediate consequence, it allows me to write down the asymptotic formula for the heavier OPE coefficient in terms of thermal 1-point coefficient. So I'll be very schematic because it's actually long. So let me unpack the notations here. So on the left-hand side, I have the OPE squared of three scalar operators with scaling dimension delta 1, delta 2, delta 3. And on the right-hand side, I have a summation over the primaries in the theory, where BO is the thermal 1-point coefficient, and Z is some emergent cross ratio, which I will define later. And the Z is restricted to go to sit between 0 and 1/4. And this G is some complicated function of delta 1, delta 2, delta 3, and F. And what is F? F is the free energy density of the CFT. Okay, and this asymptotic formula is only valid in a particular scaling limit. Now let me define the scaling limit. So this valid when, of course, all deltas are large, but delta 3 is supposed to be larger, it's supposed to grow faster than delta 1 and delta 2. So here R is a parameter that I will later send to infinity. Okay, this is the first result I will try to explain. And if I have time, I will also aim to say a few things about the mapping class group invariance and 3D CFT.
Can I ask a question? So
Yeah.
in 2 dimensions, first, you can write down modular invariance constraint, and then you have a choice. Either you can study it numerically or you can start deriving some asymptotic results.
Right.
In this case, is there some
This
good equation
Mhm.
which you can choose to study asymptotic results, or can you are limited only to asymptotic results?
right now, I only have asymptotic results. So
in principle.
in principle, it's possible to also generate numerical results, but that's like maybe in the future when we jump through some technical hurdles. Okay, let me start by explaining how to parameterize the flat conformal structures on our genus 2 manifold. I have two different ways of gluing the manifold, and we'll start from the right-hand side. So on the right-hand side, I should think of, in order to build such a genus 2 manifold, I should first take two 3-punctured sphere and glue the 3 punctures by some cylinder of certain length. This is what I call a sunrise decomposition. And maybe I can start slow and explain what do I mean by gluing a cylinder. So let me first explain what do I mean by gluing a single cylinder. So let's take two flat space, RD. There's another RD. And from it, I will remove a ball, a d-dimensional ball with radius r. And remove another d-dimensional ball with radius r. Now, the boundary of these two d-dimensional balls are two d-1 dimensional spheres. What I will do next is to glue the two d-1 dimensional spheres by a cylinder with length by e. And then I will have some shape like this. So now I want to cover this shape by two different coordinate charts. The first chart covers the upper flat space and the cylinder itself. Okay. This chart coordinates I call xt, x top. I will use the map xt to basically take the upper chart to another piece of xt.
Can I ask a basic question about geometry, just I'm not very used to genus 2 in 3 dimensions, for example. So the pictures that you have there, if I imagine those torus we saw with tori,
Yeah.
That's not an example, right?
That's not an example. That's not an example.
That's not a 3D genus 2 surface.
Right. For 3, sorry, maybe I should clarify it in the beginning. So for each of this shaded circle, you're supposed to think of it as an S2 instead.
Not a ball.
Not a D2. But if you like, you can imagine this to be a D2, but like take two pieces of them and then glue them like by the boundary of, because if you take two pieces of D2 and then glue them by the equator, you have an S2. But the important point is that this is not a solid.
So in 3D, it's not a solid product.
It's not a solid.
But since it's 3D and we can visualize, is there a picture we could see?
Oh.
See in 3D what we are.
I will be able to. I will draw like a more realistic picture in 3D later when I explain the so-called dumbbell channel decomposition. So let me start with the sunrise channel. So I have an upper chart, which I want to map to another piece of RD, where outside of this removed ball, I don't really need to do anything. I just take the flat space to the flat space itself, right? But like you want to ask, what happens? What do I need to do to the cylinder in order to map the cylinder to the flat space? The answer is I'm going to use the cylinder to plane map, so that I can flatten the cylinder down to an annulus. The shaded region is the annulus. It's going to be the image of the cylinder. Yes.
Just in case for some confusion, for 3D CFT, this cylinder is 4 dimensions.
No. For 3D CFT, this is R3, and this circle represents a 2 sphere, and this cylinder is still a 3-dimensional cylinder. because the section is a two-sphere, and then
Okay.
similarly, on the lower chart, X bottom, I can play the same trick. So the lower half, sorry, in the exterior of the removed ball, nothing happens, but in the interior of the removed ball, I'm supposed to squeeze the cylinder down to an annulus. Right. So,
We need to do some smoothing where the.
oh yeah, that's a good point, because there will be non-smoothness in the geometry, and I will have to take care of the non-smoothness by introducing some extra factors. Right. So any point in the cylinder is covered into.
There's no trace in the geometry.
Okay.
Well, I mean, there's no
Here.
smoothness in the left picture, but that's not, that's not big. We're reducing the charts here. So there is no, like, these corners, they are, I mean, they're not corners in this Cardian charts. So it's just, like, there is no smoothness.
It's not the same map outside the disk.
Yeah. So outside the disk, everything is identity. Inside the disk, you have the cylinder to plane map. So there is like a abrupt change in the at the boundary there.
Yeah, sorry. If you look at the definition of a manifold, the only thing that's required to be smooth is transition maps between two charts. Here, the transition map should only be defined on the animal, so it's smooth.
And the transition map is indeed smooth, but the coordinate function itself is not smooth.
No, sorry.
Did you see?
Coordinate function cannot explain what coordinate function. When coordinate function is smooth, I do define the smooth structure. You're defining the smooth structure. Smooth structure is defined very same than its coordinate maps are.
Topologically, it's a manifold, but the metric may not be smooth. Whatever you.
That's not metric.
There's probably something, probably
metric
needs
is a
the
metric
metric,
set.
probably she needs this other geometry, that other metric for some purposes, which we don't know yet.
Yeah, I agree that it should be a manifold.
Okay, so, all right, but so what I'm gonna do next
Yes,
is,
why did you start with the left picture? Why did you not start just with the right picture? Why did you not say, let me take two copies of RD with this annulus, let me just glue along the annulus and that's it? Why did you not start with this?
you can certainly do it, because I want to like introduce the idea of, you know, you have a shape where you want to cover by coordinate charts.
You have some choices to make, right? You started with this picture on the left, not on the right. Started on the right, then you would have avoided speaking about singularities. Is there a reason why you did not start on the right?
Not really, but I do think that the issue of non-smoothness or singularity is still there.
But on
Yeah,
the right.
wait, so. Sorry, I'm sorry to be like, but you have two charts. The
Yeah.
transition map is smooth, and
Yeah.
it's a conformal map as well.
Yes.
So that means that the conformal structure is smooth. You have smooth manifolds. Where is the singularity?
The fact that the XB is defined in two different sections. Outside of the annulus, it's just the identity map. But inside the annulus, I have all of a sudden I turn on this plane to cylinder map.
Yeah, but for all intents, first thing on the left is a topological space.
Right.
You're defining what the smooth structure is. So there is no point in discussing what happens with map XP because you're defining the smooth structure such that even though it looks like it's piecewise smooth, it's actually entirely smooth. So you're defining charts, and one thing you should care about is the transition function. The transition function is smooth and conformal. So from structure and smooth structure don't have any issues. So what is singularity discussing?
Okay, maybe let me put it in this way. So what I'm trying to do here is to parameterize the flat conformal structures on such a shape or such a manifold. But if you try to write down metrics on such a manifold, then you will have some.
Metrics and structures. Yeah, okay, if you're talking about metric, I agree the metric will not be smooth.
Um,
But
But I agree this is a the important point, but I'm not sure we should hash it out.
All right.
For the other people on the group. I
What that you're after feedback.
All right, so
It's important because maybe, then, for example, one could answer that I would like to look on geometry on the left because it has some special properties, reflection, sensitivity, whatnot. That would be a valid answer, which you did not provide. You just said, you did not provide us an answer why you, for example, also on the left, you could.
think that
Why that is an important
Well,
technically, right?
well, we will see how the talk goes. At the end of the talk, we will see if this picture of the left will be necessary or not.
We will have to guess it ourselves.
You're a smart person. I'm sure you'll make the right guess.
all right, so fast forward and write down the transit. So every point in the cylinder is going to be covered in two different charts. And here is the transition map between the two charts, two coordinate charts. And this is going to be, importantly, this is going to be an orientation reversing conformal transformation. All right, so all of this is to understand how to glue a single cylinder. Now to write down the so-called sunrise channel decomposition, I have to glue 3 cylinders at the same time. So to do this, I have to give you a triplet of orientation reversing conformal transformations. But if I do a global a coordinate transformation on xt or a global transformation, no, a global conformal, sorry, a global coordinate transformation on xp, then I'm just reparameterizing my plane without actually doing anything. Therefore, such coordinate transformation should be counted as some kind of redundancy. So I should define the equivalence relation, saying that and from here, we know that the moduli space of the moduli space of the flat conformal structures on such a manifold, which is topologically S1 times the connected sum of 2 S1 times SD minus 1, is going to be it's going to be given by this double quotient. Here, G minus basically means the set of orientation reversing conformal transformations.
So since your transition maps are orientation reversing, then your mechanical, at least it's not always variant. So is it orientable or not?
It is orientable. The fact that I am having, yeah, I think it's orientable. The fact that I'm having this orientation reversing map, it has to do with the fact that I'm choosing to cut and glue it in this particular way. Okay. Okay, at this point, things are still. All right, at this point, things are still very abstract because every point in the space represents the whole family of geometries. So let me commit to a particular representative geometry by writing down explicitly what is this G1 and what is this G2 and what is this G3. So. So in this particular geometry, I'm choosing to
On the first equation.
I is the inversion.
No, it's just give an index, so you don't have to write the same equation 2 times.
No, it's not really the same equation.
Looks the same.
Oh,
there's a sign.
yeah, it's not going to, sorry.
Doesn't look. This stage of the talk.
Decrease.
Fine.
So what I'm choosing to do is the following. Oh, this is a d-dimensional view. And what I'm doing is I choose to cut out a ball centered at infinity with radius 1/2.
I'm sorry, I can't see, but you're just standing in front.
Oh, okay. And I will choose to cut out another ball centered at -1 minus A2. 0. So this point is located on the x1 axis. And similarly, here. I'll just choose to cut out another ball at 1 plus A1, 0, 0, 0. And the radius of the two balls are chosen so that they are tangential to the third.
Sorry. I mean, what are these G's are what? They're elements of the conformal
They're,
group?
yeah, sorry. These G's are element of G minus, which are orientation reversing conformal.
Conformal transformations. So I know how they act on space.
Right.
Right. So I don't know what we are doing here because you have space where you cut stuff out, and now you cut out balls, but
So basically, you're supposed to
see three conformal transformations. So
you want to take two pieces of the three punctured spheres and then glue the ball you cut out by some cylinders. And this is the three G's are the transition maps within the cylinder.
Why is it important that the balls you cut out are tangent to each other?
The idea is that I want to create very short circles in the manifold, and the short circles are helpful in the study of certain kinematics. Okay.
Sorry, so I can understand that you have this. So you start with this construction where you say you have this gluing map, which is G1, so this is for like the first pole, and then three poles.
Yes.
And so you said that you parameterize the conformal structure by G1 to each three. They connect.
Quoted out
So
by.
they connect to the planes, and then you confirm to one plane and or the other. That's where you push. Yeah.
Yes.
So I understand that there's G1 to G3 parameterize different choices of conformal gluing maps, but what about the choices of the
Angular
circles, the underlying?
Yeah, so sorry. So this is a representative geometry inside the whole family of
No, I'm not asking about this picture. I'm asking why the conformal modular space is just given by counting G's. Why you don't need that extra coordinates to count the variable circles? It's not.
But the
It's not the whole modular space.
sorry. This
Is M the whole when it was space?
the M is a homogeneous space.
So my question is why doesn't it have coordinates with locations inside circles?
Well, then I can apply a conformal transformation to take the 3 points to the places I want, right?
Yeah, but the circles. You have 3 points, but you also have the three circles, right?
Yes, yeah, indeed, that's true. I also have 3 circles, and I can apply some global dilatations to dial the radius together. And I can do the following. So whenever you have two planes connected by a cylinder, what I can choose to do is that I can choose to cut out part of the cylinder and then flatten it onto the plane, onto the lower half plane and onto the upper half plane. So that if I do this, this is a file map. But if I do this, I can make the cylinder shorter and make the circle larger. So that tells you, unless you fix the radius of the ball you removed, it doesn't make sense to talk about the length of the cylinder. So here I'm specifying the length of the cylinder by fixing the radius of the ball there. Make sense? Okay, cool. Oh, sorry. The H1, H2, H3s are the angular twists. They are elements in SOD. Sorry. Okay. All right, so a lot to say about the star channel composition. Let me move on to the
That's great. You might not have a lot of time left, right? I mean, technically, we're almost there. Technically, you have 3 minutes, but there are lots of questions, but I'm not sure, right? What do we see now? We have some geometry. You described for us that you have a good way to understand the conformal margin, like the space of conformal structures on this manifold, right?
okay, I have 3 minutes. Let me see how much progress I can make. So maybe I will be able to finish in the 3 minutes. So
Better to skip to say, look, there's a conformal structure, you have an equation, but you wrote what it's good for. Don't you want to go into the physics and say, at least one of the channels we can understand now.
right, so good. So these two different pictures, these two different channels give us two different decompositions of the genus 2 partition. So here, as I've explained, what I want to do in writing down the sunrise channel decomposition is to insert a bunch of resolution identity here in this cutting sphere, in this cutting sphere, and in this cutting sphere. Then by doing that, I will have the following sum. There is a bunch of factors that I don't have time to explain, but I'm happy to talk about it later. So basically, I will have a pair of 1-point function where the inversion points are on the centers of the 3 balls. So, and you can imagine I can that I can factor out the OP coefficients from these 2 3-point functions. And that's why you have hoped to get such a factor. This is a contribution of the primaries, but of course, as always, I need to add the contribution from all the descendants. And as I explained before, I factor out C squared from these two 3-point functions, and then package the rest as a kinematic object, which I call genus 2 block. Then I will have this particular composition. So what is this B? B is, as I explained, it is a genus 2 block. And the nice thing about it is that it satisfies also the following orthonormal relation. Proportional to delta 110. I will be schematic. Now, from the left-hand side,
What does that mean? Means that these genus 2 blocks are
also orthogonal to each other, and this integral is so this d mu is a measure on this moduli space, and this 1 tilde, 2 tilde, 3 tilde are the shadow representations of 1, 2, and 3.
underrated 1, 2.
And yeah, so 1, 2, and 3 is basically delta 1, comma lambda 1. Okay, so you can at this point you can probably imagine what I'm gonna do next. So I want to write down the so-called dumbbell channel decomposition of the genus 2 partition function. I'll just write it like very quickly. Okay, here I have two parameters, the beta and HM. Beta is basically the length of the connecting cylinder, and HM is an angular twist I insert here. Right, this is going to be the dumbbell channel decompensated for the GS2 partition. So what I'm going to do is to investigate the particular kinematic limit of this geometry. And in that limit, I will take the radius of the two SD minus ones to be infinity. And in this limit, the 2S1 times SD minus 1 will basically become RD minus 1 times S1. And in this case, the thermal one-point function will, the expression of the thermal one-point function will greatly simplify. And we have something like,
Do you have basically a crossing equation for arbitrarily moduli? You don't need to take a limit. You have something that's well defined at the sharp for.
right, so this equating this expression with this expression is going to be the full-fledged genus to crossing. But to get something that's quote unquote useful, I want to examine it at a particular kinematic.
Yeah, but in principle, we would say, give this to SDPP and try to do a genus.
Oh, but then you will have to compute this B12, the genus two plot, which is technically difficult.
Yeah,
but it's
we
doable.
managed to compute conformal blocks at some point, and people would say the same thing about conformal blocks.
Yeah, sure. In the near future, or far future, I'm pretty confident we'll be able to put this such a crossing equation into SD.
Maybe
But
we'll-
at the
if
first,
it's complicated, maybe we'll have the Simon's collaboration on Jesus.
that would be amazing. But like the first line of it, and the first line of attack is to look at a simplifying limit of such a crossing equation, and that simplifying limit is when the 2SD minus 1 becomes RD minus 1, so that the 1-point function becomes easier. And then I can use
Bob's question before the limit. Do you have possibility to download?
do I have positivity in the dumbbell channel?
Because it's the 1-point function value that they're going to use. These.
Right, that is true. Why do you worry about positivity?
Because now you can dominate the system by adding some extra stuff.
Well, see,
we expand this 1-point function.
In terms of the 3-point.
Yeah.
In terms of thermal 1-point block and the 3-point coefficient, you have that's a quadratic expression.
I mean, you see square there, so.
Oh, but that comes from the thermal the thermal space.
Yeah, they're not squares there. They're just copy a couple of coefficients out.
I mean, the square.
Okay.
Yeah.
No, but that's just going to be some positive sum of that matrix.
It is positive. There's some positivity on there. Yes.
It's a very big matrix.
I guess I used up my 3 minutes.
Yeah, I guess so. We kind of see how you get this question. I'm not sure if you have an outlook or whatever. Because now I at least understand what how to get to that equation.
Right. So going from here to that equation that I wrote above, what we need to do is to use this orthonormal relation to invert the genus two block decompositions. By basically integrating the left-hand side against the shallow.
May I ask a question?
Yeah.
So in this paper by David and many others a few years ago,
This one.
it might be that one, yeah, absolutely. And so there was this hotspot hypothesis and so on.
Right.
To me, it seemed a bit unjustified. Does this show that that hypothesis is correct, or it still relies on that hypothesis? And do we have evidence for that hypothesis?
Well, I think from the dumbbell channel decomposition of the GS2 partition function, it gives a consistent result as the hotspot extension. basically, what do I mean by that? Well, in the thermal flux space limit, I will have times some other functions. This is an unnormalized thermal. And in the we know that in the thermal flux space limit, the normalized one-point function is given by some VO over beta to the power delta. So then you have to evaluate this trait, you have to multiply it by some partition function on S1 times S1. And you can reproduce the same factors, d beta L and d beta R, from the hotspot. So in this sense, it is consistent with the hotspot. I'm not sure if this makes sense. You can think of each of these vectors as given by the contribution of the hotspot in this geometry.
But it's not a proof. It's just
It's not a proof. It's evidence that it's a piece of evidence which says the hotspot conjecture is consistent with the other experiment.
and that result that you derived, it's a derivation or it's assuming that I got this one?
I do have to use thermal effective action, but I just need to plug in the thermal effective action into the expression of Z beta L and Z beta R. I do not have to directly use the hotspot conjecture.
Yes, I'm a little confused with the logic, but so in certain limit of the modular, you can evaluate the left-hand side in terms of
Right.
functions, but I thought you said you had to do an integral over the modular. Are you saying that that's like tangent dominance?
Yes. So when we evaluate the inversion integral, we're using saddle point approximation, and that saddle point that particular saddle point is the right. At that saddle point, we're still in. To evaluate the block in that saddle point, we can still using our simplified assumptions. Yeah.
Any comments about this mapping class group invariance?
Good. So in 3D, you know that mathematicians have worked out that the mapping class group of
I think it should not. It's not recorded otherwise.
Oh.
Sorry. You have to be inside the two lines there.
I see. Sorry. So the mapping class group for connect the sum of S1 times S2. Here I'm restricting to 3D. Is the outer automorphism group of F2. F2 is the free group of two generators. And semi-direct product Z mod 2Z to the power 2. Now this group happens to be isomorphic to GL2Z. It's a little bit abstract, but let me explain what the generators of this group do. So this Z mod 2Z raised to power 2, they generate the untwist across the two uncontractable circles. So let's call this circle A, and let's call this circle B. I'll read it in a different way. This is A, this is B. So generators of this factor, do I have to explain what a Dern twist is?
I think you don't have time, so.
Oh, okay, so they generate Dern twist and they don't really do. So
Maybe you should just say, what's the new results?
the new result is kind of disappointing in a sense that you can see explicitly that using either dumbbell decomposition or the sunrise decomposition, that the action of the mapping class group preserves the GS2 partition function.
Term by term.
Right. Term by terms.
Thanks. I think we should leave it at, sorry, but it's the second time.
Well, we can discuss this later if you have further questions.
It wants to know the results.
I see.
We're way over time, so.
Oh, sorry.
A very nice stuff.
Okay.